Now let's look at a scenario where we model something with a linear differential equation rather than an autonomous differential equation. Right? So we're going to construct a differential equation that models the amount of tars in an airport smoking lunch. Okay. So I wrote assuming the peak at noon and the lowest point at midnight, meaning that the people smoke most of all at noon and least of all at midnight. So at midnight it's going to be empty, no one is going to smoke. So here is what I'm going to assume. So that first of all, that the volume of air in the smoking lunch is 90 cubical meters. It's a bit generous, to be honest. So usually smoking lunches are smaller than that, but let it be 90 cubic meters. Then we're going to assume that there is a steady inflow of air, of clean air. This number, 10 cubic meters per hour, is just made up. I have no idea what the real number is, but of course, the logic here is fine. So anyway, there is a certain steady inflow of clean air. Then when people smoke in the lounge, tars are added to the clean air in certain concentration that depends on time. So this function C of t is supposed to model the periodic change in, periodic addition of tars due to people smoking. Well, periodic, meaning that every day it happens in exactly the same way. Okay? So t is the time measured in hours. So t plus 24 is the same time the next day. So, and we are assuming that this is a periodic function. Well, and then just to come up with a periodic function that has points of minimum, when t is 0, 24, 48, and so on, that is midnight, and points of maximum, 12, 36, and so on, that is noon. I just thought of the simplest trigonometric function, and that's what we are going to do. Again, the real function is probably not that simple, but the logic is fine. Right? So here, C of t, the minimum point is, the minimum value is 0, the maximum value is 1. So it looks like this. So the graph of the function C of t looks like this. So this is 0, 24, 48, and so on. This is 12, 36, 60, and so on. Well, then we also assume that the outflow is the same, 10 cubic meters of air per hour. Well, otherwise it wouldn't add up, So the inflow should be the same as the outflow, so that the amount of air is the same. But then we are assuming that what is flown out is actually the perfect mixture of tars with clean air. So let y of t be the amount of tars in the air by time t measured in, say, milligrams or micrograms. I don't know how exactly it is measured, but in some units of weight. And so in general, if we take the derivative of the amount of tars, that's the rate of change of the amount of tars, which adds up from rate in and rate out. So rate in minus rate out. So rate in due to people smoking, and rate out due to air flowing out of the smoking lounge. So rate in is concentration times the inflow. So the concentration here is our function C of t. And inflow is 10 cubic meters. Then the rate out, is again concentration times the outflow. Concentration is the existing amount divided by volume times the outflow. So the existing amount is actually Y. Volume is 90. Outflow is 10. So let me write it down that existing amount. So volume is 90. Existing amount is Y. And outflow is 10. And so Y divided by 90 times 10 is Y over 9. That's how we got this. And then putting it together, we get this differential equation. So then, if we plot the direction field, we are going to see that, well, there is some oscillating behavior, but it's very hard to understand what's going on exactly here. So we're going to have to solve it. So let us solve this differential equation. It is a linear differential equation, so we're going to move this term to the left-hand side. Right? So then we are going to multiply it by the integrating factor. So that's the coefficient at y. So the integrating factor is going to be e to the power integral of 1 over 9 dt. The integral of 1 over 9 is t over 9, so this is e to t over 9. And that's what we did. So that's the integrating factor. And then we are going to multiply by the integrating factor. And now the left-hand side, so the reason we did it is because now the left-hand side is e to the t over 9 times y, everything prime. Well, but then, since we found the derivative of this function, e times, e to the t over 9 times y, it means that the function itself is going to be the antiderivative. And of course, you can try to find it by parts 2 times. Well, if you like integration by parts, yeah, please go ahead. I have done it probably thousands of times in my life, so I just, yeah, did it on Wolfram Alpha for the sake of this lecture. Here is the answer. Well, it is probably not a very pretty answer, but you could again feed it to Wolfram Alpha, well, and then simplify it. I mean, instead of writing it as the sum of two trigonometric functions, it could rewrite it with amplitude and phase, like just one coefficient times the trigonometric function with some shift. Well, anyway, you can plot the graph no matter what, regardless of how it is presented. So my main purpose is to show that this is a periodic function, and this part just goes to 0 when t approaches infinity. It means that eventually, no matter what the amount of tars was initially, eventually the amount of tars is going to just oscillate according to this periodic function after a few days. And then, for example, you can find, I don't know, you can find the exact moment when there is the least amount of tars in the launch, or the most amount of tars. So note that it's not when people smoke most or people smoke least. It's a bit later, so there is a delay here. Well, and so on and so forth, right? So that's how we can model a general situation where some substances are mixing together. And then I would like to say a few words about the domain of an ordinary differential equation, or the solution of an ordinary differential equation. Probably the easiest example to think about is, what if we want to model the Singapore population growth according to the logistic law? So it means that we set up the logistic equation. So here, note that I assume that the carrying capacity is of Singapore is 7 million. There is no reason to say that. It's just some number. Well, but Singapore history started in 1965, so if t is time measured in years, then what we have here is that the initial point is p of 1965 is 1.9 million. Right? So the domain of this differential equation is the set of values of the dependent variable and independent variable that make sense. So here the population should be non-negative, right? Otherwise it just doesn't make sense. And the time for this particular application, so the time is bigger than or equal than 1965. So then there could be an alternative model to do the same thing. Note that the main idea is still the same. So the thing about this function is that here the equilibrium solutions are also p equals 0 and p equals 7, and 0 is unstable, 7 is stable, so it's kind of the logic is similar. Well, and the domain would be similar too, only probably now p has to be strictly positive, because otherwise there would be ln of 7 over p, and if p is 0, then it does not compute. So, but in the next lecture we're going to assume that the domain of a differential equation is an open subset of the plane. So the set of all possible feasible values of t and y. I mean, although for specific applications, the set of feasible values of t and y could be, could come from the problem. But theoretically, for mathematics, it is always more convenient to assume that the set of feasible values, it forms an open subset of the plane, right? And then the solution is a differentiable function defined on an open interval. That is also important. So the idea is that the differential equation, it models a continuous process, like something is growing or something is moving, which means that the set of all possible values of t should be an interval. Okay, so for instance, here it would be more convenient to assume that rather than assuming that p is bigger than or equal to 0, it is more convenient to assume that p is strictly bigger than 0 and t is bigger than 1965 minus certain epsilon, just to